Today, we're going on an incredible journey. We're going to follow the story of fuel, all the way from a black liquid buried for millions of years, through a massive chemical refinery, right into the explosive heart of an engine. Let's dig into the chemistry that literally powers our world. You know that feeling, right? You turn the key, you hear that roar, you feel the car accelerate. Well, all of that comes down to a series of incredibly fast, incredibly powerful chemical reactions. Today, we're going to pop the hood and see exactly what's going on in there. So, here's our roadmap for this explainer. We're going to start at the very beginning, millions of years in the past. Then, we'll see how that raw material gets sorted and even chemically hacked to make the perfect fuel. After that, we dive into the explosive moment of combustion, and finally, we'll have to face the environmental consequences. All right, so the story of the fuel in your car doesn't start at the gas station. It starts millions and millions of years ago, with ancient life buried deep, deep beneath the surface of the Earth. This is our starting material, crude oil, and the key word here is hydrocarbons. These are just molecules made of hydrogen and carbon atoms, but they're linked together in all sorts of different chains and rings. It's basically this massive, messy chemical soup of stored-up solar energy from a time before dinosaurs. And here is the single most important fact about this chemical soup: we can't make any more of it. It took nature millions of years to cook this stuff up, which makes it a finite resource. Once it's gone, it is gone for good. And that simple fact, well, it underpins our entire global energy economy. So, you've got this black, gloopy mixture. How on earth do you turn that into useful fuel? Well, that brings us to our next chapter, the Great Separation. The whole process is called fractional distillation, and the core idea behind it is, well, brilliantly simple. It all comes down to one key physical property: boiling point. You see, smaller, lighter molecules turn into a gas at lower temperatures than the big, heavy ones. So if you can control the temperature, you can sort them out with amazing precision. Okay, so here's how it works. Picture a massive, tall tower. The hot crude oil is pumped in at the bottom and it vaporizes. As all these vapors start to rise, they begin to cool down. The really big, heavy hydrocarbons, the ones with high boiling points, they turn back into a liquid first, way down at the hot bottom. But the smaller, lighter ones, they keep rising higher and higher until they reach a cooler level where they finally condense. It's like a skyscraper of temperature, and each different fraction gets off at its own specific floor. And what you get out of this process is just fascinating. The really small molecules, with around 8 carbon atoms, they're super volatile and flammable, which makes them perfect for petrol. The mid-sized chains, maybe 15 carbons long, they give us diesel. And the truly massive molecules, with over 35 carbons, they're so heavy and dense they're not even a fuel. They become bitumen, that thick, sticky tar we use to pave our roads. But there's a problem with fractional distillation. You see, we often get way too much of the heavy stuff, like that bitumen, and not nearly enough of the valuable, high-demand stuff like petrol. So what do? Well, you hack the hydrocarbon. This is just a classic supply and demand problem, right? The world wants petrol for its cars, but crude oil gives us a whole mix of everything. So chemists had to come up with a really clever way to rebalance the scales. And the solution is called cracking. And yeah, it does pretty much exactly what it sounds like. You take those long, not-so-valuable hydrocarbon chains, you heat them to incredibly high temperatures. We're talking around 650 degrees Celsius, and you pass them over a hot catalyst. Now, a catalyst is just something that speeds up a chemical reaction without getting used up. In this case, it helps to literally crack those big molecules into smaller, much more valuable ones. So cracking is absolutely crucial for 2 big reasons. First, of course, it solves that supply and demand problem, turning less useful stuff into the high-demand petrol we all need. But second, and this is a huge takeaway, it also creates a special type of molecule called an alkene. These alkenes are the fundamental building blocks, the feedstock for the entire modern plastics industry. So the very same process that fuels our cars is also making the material for everything from your water bottle to Lego bricks. All right, so we've created the perfect fuel. Now it's time for the climax of its journey. The moment it all happens, the moment it's burned to release all that stored energy. This is combustion. But here's the thing, not all burns are created equal. If you have plenty of oxygen, the fuel undergoes what we call complete combustion. It's a really clean, efficient burn. It produces just carbon dioxide and water, and you get the maximum amount of energy out of it. But If oxygen is limited, you get incomplete combustion, and that is a dirty, inefficient burn that produces some seriously nasty byproducts. One of those nasty byproducts is carbon monoxide. This gas is so toxic because it's actually better than oxygen at sticking to the hemoglobin in your red blood cells. So when you breathe it in, it essentially hijacks your blood's delivery service, preventing oxygen from getting where it needs to go, and that can be fatal. The other major byproduct is soot. Now, this is the stuff you can actually see. It's basically just tiny black particles of pure carbon. It's the visible part of a dirty burn. That black smoke that coats buildings in grime, and if you breathe it in, can cause serious respiratory problems. But soot and carbon monoxide, they aren't the only problems. The final part of our story deals with the invisible aftermath, the pollutants that cause widespread environmental damage. It's so easy to focus on the black smoke you can see coming out of an exhaust pipe, but some of the most harmful pollutants that are released from burning fuel are actually completely invisible gases. Let's trace the chain reaction that creates acid rain. It starts with tiny amounts of sulfur that are just naturally present as an impurity in fossil fuels. So when the fuel burns, this sulfur reacts with oxygen to form a gas called sulfur dioxide. That gas rises up into the atmosphere, dissolves in the tiny water droplets in clouds, and forms acid. And when that rain falls, it's acid rain. And the effects of acid rain are devastating. It literally corrodes buildings and statues, especially ones made of limestone. It damages entire forests, causing trees to lose their leaves and die. And it can make whole rivers and lakes so acidic that fish and other aquatic life just can't survive. There's another major invisible culprit here: nitrogen oxides, or NOx for short. Now, what's really interesting is that these don't come from the fuel itself. They actually form when the crazy high temperatures inside an engine force the nitrogen and oxygen from the air around it to react with each other. And NOx also contributes to acid rain, as well as that photochemical smog you see hanging over big cities. So, after all that, where do we go from here? Well, this quick comparison might offer a clue. Just look at petrol versus hydrogen. For every kilogram, hydrogen releases over 3 times more energy, and its only combustion product is clean, simple water. Which leaves us with this one final massive thought. For over 100 years, our entire civilization has been built on the incredible energy packed into hydrocarbons. We've seen their amazing journey, but we've also seen their serious consequences. So the question now is, what will we build our future on?